infrastructure management has always been driven by tools. Tools to provision, tools to configure, tools to scale. For years, infrastructure as code has been the standard. We write templates, define state, run plan, and apply. And yes, it works. But in today's fast-moving world, that approach feels rigid. Engineers spend more time learning DSLs and memorizing commands than actually solving problems. Now, imagine if you could just describe what you want and an intelligent system takes care of the rest. That's the promise of agentic AI in DevOps. And in this video, we'll explore why this shift matters.
Right now, the reality of AI in DevOps is actually pretty limited. Most engineers use Gen AI just to generate Terraform modules. That's it. Then they run Terraform plan, followed by Terraform apply, and the resources come up. The workflow? Still the same as before. Some teams did try to push further. They tested AI agents in different scenarios, but more often than not, the results didn't live up to expectations. And the reaction was predictable. These tools don't really work. Let's stick to the old way. Now, here's the key point. Even if we had fully autonomous agents today, we wouldn't just jump straight into one-click infrastructure. For a long time, we'll still need that plan and act cycle. Not just for safety, but for certainty. Engineers want to see what's about to change before it happens. Only after enough trust is built and enough confidence in correctness will we move to a world where infrastructure is provisioned in a single step without human confirmation. That shift won't happen overnight. It's going to be a journey.
So why do so many teams walk away disappointed after trying AI in DevOps? Well, a lot of it comes down to a common misconception. The idea that moving from traditional DevOps to agent-handling AI is a single step, something you can do in a day or maybe a week. Just flip a switch and suddenly your infrastructure is fully autonomous. But let's pause for a second. Does that really sound realistic? Could any transformation that deep happen overnight? Of course not. The truth is, we're still far from fully autonomous agents. This isn't a quick jump. It's a journey. And like most real transformations in tech, it's going to take time, probably years. And that's because the evolution of large language models themselves is going to take years before they're ready to handle that level of autonomy. So the real question is, what can AI agents do well today? Actually, quite a lot if we use them in the right way. Large language models are already excellent at natural language processing. They're good at producing structured outputs. They can take a plain English request and translate it into something machine-readable. That's a real strength, and that's exactly where phase one of this journey begins. But here's the catch. When it comes to execution, the act phase, these models are unreliable. We've seen them generate a plan and then fail to follow their own instructions. Sometimes they skip steps. Sometimes they hallucinate entirely new ones. And would you really trust that kind of behavior in a production environment? Definitely not. So the realistic approach is clear. We lean on LLMs for what they do best: planning, reasoning, structured outputs. And we hold back from letting them execute directly until the chances of mistakes come close to zero. That's phase one of the journey. Later, as the models evolve, we'll move closer to autonomy. But for now, Agent AI is about working with engineers, not replacing them. Let's take an example to make this concrete. Suppose you're using an AI agent powered by a reasoning LLM with a web search tool built in. Now, you throw in a simple request. Provision an EC2 virtual machine with T3.micro instance type and an elastic IP address. What happens next? Well, ideally, the model should ask you for the operating system image, because without that, the VM can't be created. Once you provide it, the agent should reason through the request and generate 3 separate commands to fulfill it. Sounds good in theory, right? But here's the problem. The time it takes depends heavily on the model. A top-tier LLM like Claude Sonnet 4 or Gemini Pro 2.5 might eventually get there. But even then, the chances are high that it won't work or it will take too long. And if you rely on smaller models, the success rate drops even further. So what's the alternative? Instead of throwing vague, high-level prompts into a reasoning LLM and hoping a web search pulls in wrong or outdated information, we can take a different route. We craft a low-level prompt with clear instructions. We ask the agent to simply convert those instructions into a structured format. No heavy reasoning, no risky search tool. And here's the clever part. We use a cheaper, non-reasoning LLM, one that's really good at structured outputs. We feed it the exact documentation it needs, and that's it. The benefits? Two big ones. First, it costs less because we're not burning expensive reasoning cycles. Second, it responds faster and more accurately since we're not relying on unpredictable search results. And once we have that structured output, we don't even need the LLM to execute. A simple Python program can handle the provisioning directly, which means no hallucinations in the act phase and a workflow that's both reliable and efficient.
Terraform, like any script, is built on a rigid approach. It starts with the desired state, written in .tf files. Then the process is always the same. Run Terraform plan, then run Terraform apply, and only then are the resources provisioned. No shortcuts, no flexibility, just the same sequence every single time. Now, here's where the rigidity really shows up. Imagine making a tiny change, like adding a simple tag, tag1, to resource 1. Sounds like it should be quick, right? But Terraform doesn't work that way. During the plan phase, it compares every resource in the desired state against every resource in the state file. Only after this exhaustive check does it figure out the difference and prepare the change. And depending on how many resources you're managing, that comparison can take a lot of time, even if all you wanted was a single tag.
So what happens when you throw a desired state directly at an AI agent? On the very first run, it looks a lot like Terraform. You provide the desired state, the agent processes it and provisions the resources. Nothing magical there, but the difference is in how the agent handles updates. Now imagine you update the desired state with a small tweak, like adding tag1 to resource 1. Terraform would run its plan phase, compare every resource in the desired state with every resource in the state file, and then decide what to change. That's slow and rigid. An agent can do better. It could, for example, run a quick git diff between version 1 and version 2 of the desired state. By focusing only on what actually changed, the agent identifies the required update much faster. But here's where things get even more interesting. Instead of always passing the full desired state, you can throw only the delta, the exact change you want. For example, a simple prompt, add tag1 to resource 1. In this case, the agent doesn't need to reprocess everything. It can just take the delta, update the desired state in Git, and apply the change directly on the target resource, all without the overhead of scanning the entire configuration. Terraform is rigid, always tied to full state comparisons. AI agents are flexible. They can work with the whole state or just a change, whichever is optimal. That's the real advantage of agentic AI.
When it comes to managing AWS infrastructure, the choices are endless. You've got the AWS native tools, Console, CLI, SDKs, CloudFormation, CDK, even MCP servers. And then there are the cloud-agnostic ones, Terraform, OpenTofu, Pulumi. On the surface, that might look like flexibility, but here's the catch. Each of these tools comes with its own DSL, its own syntax, its own way of thinking. So even for a simple task, like creating a VPC, the commands and concepts differ wildly across tools. Now, imagine you're working with multiple clients. Each one uses a different set of tools. So every time you switch, you need to relearn how to do the very same thing. And the result, cognitive overload and wasted time. This leads to an even bigger problem. As a DevOps engineer, you spend months, sometimes years, mastering a tool like Terraform. You get certified, you become an expert, but then you're seen as a Terraform DevOps engineer. So when a job comes up that requires Pulumi or CloudFormation, you're often not even considered. And this isn't rare.
It's something that happens in IT services companies all the time, especially in India. The tools you master can end up defining your career path. And that's a trap many engineers don't even realize they're walking into.
When it comes to agentic AI, you really have to start from scratch. You can't just take the old infrastructure as code patterns and hope they will fit. Instead, you need to ask yourself, what would it look like if you designed workflows that actually take advantage of the superpowers of modern large language models? Think about the difference in how you give instructions. With an IaC tool, you have to learn its DSL, its unique syntax, its quirks, and its rules. But with an agent, you don't have to restrict yourself to one language or format. You can provide a plain English prompt. You can provide a YAML or JSON file with structured instructions. You can even upload a screenshot of an architecture diagram. And yes, you can combine both text and image together. The agent does not care whether your input is structured or unstructured. But here's a practical tip for you. If you want predictable and consistent results, stick to structured inputs like YAML. That way, even if the same request can be phrased in multiple ways in plain text, you will always get the same schema-driven output. Now, let's talk about execution, because this is where the experience really changes for you. With an IaC tool, when you kick off a long-running task like provisioning a virtual machine, you wait. You watch the process complete before you can move on. But with an agent, you can work in fire and forget mode. You simply issue the request. The agent provisions the VM in the background. When the cloud provider API notifies the agent that the task is complete, it immediately continues with the next dependent step. For you, that means high-performance asynchronous provisioning without you lifting a finger beyond the initial instruction. And the same concept applies to scaling. Instead of bolting on Kubernetes add-ons and learning AWS-specific tools for horizontal and vertical scaling, you let the agent handle it. Monitoring tools feed real-time events. Maybe a node went down, maybe CPU usage spiked. The agent processes those signals and adjusts capacity automatically with a universal approach that works across environments. No special hacks for Kubernetes, no AWS-only tricks. But here's what really sets an agent apart. It isn't limited to provisioning infrastructure like an IaC tool. It can do much more. For example, you can query your resources directly. Want to know which VPCs don't have flow logs enabled? Just ask, and the agent will tell you. You can also calculate pricing, not just for a single resource, but for the entire stack. This helps you weigh trade-offs before you commit changes, something every DevOps engineer struggles with today. Then comes the routine work. Instead of juggling multiple CLIs with their own syntax, the agent can replace them for most day-to-day operations, so you don't have to memorize a dozen different commands for different tools. And finally, when it presents results, it doesn't just dump raw output at you. It can display information in a clean visual way, tables, searchable lists, filters, even charts for cost breakdowns or performance trends. For you, that means faster insights, less noise, and a much better developer experience. So unlike IaC, which narrows your role down to learning DSLs and managing provisioning, Agentic AI opens the door much wider. It gives you flexible inputs, asynchronous execution with scaling built in, powerful querying, pricing visibility, and polished outputs you can actually act on. And as a DevOps engineer, that means less time wrangling tools and more time solving real problems.
While Gen AI is powerful, it has also opened up new doors for attackers, and as a DevOps engineer, you need to be aware of them. Let me ask you this. Do you know where your credentials are stored right now? Chances are they're sitting in your .aws folder, or in your .ssh folder, or maybe inside a .env file. They're scattered in multiple places across your system. Now, here's the surprising part. Why are most CLI tools still relying on service accounts or long-lived credentials? Why aren't they using OAuth or OIDC to issue tokens that expire in 30 minutes or less? It's almost like we're handing attackers a free pass. And attackers know it. They are actively targeting AI-powered CLIs like Claude Code or Gemini CLI.
Think about it. These tools depend on AWS CLI and others to talk to third-party APIs. So if your credentials are in .aws or .ssh, guess what the attackers go after? Exactly that. And this isn't just a theory. We've already seen it happen. Remember the NAX package? It's a widely used open-source build system. Hackers compromised it in a supply chain attack and managed to steal cryptocurrency wallets, GitHub tokens, NPM tokens, SSH keys, you name it. And here's the scary part. Anthropic recently reported that attackers are now using AI itself to speed this up. So what used to take weeks or months can now be done in days, sometimes even hours. Do you see the shift? The threat isn't in the future, it's already here. So the real question is, how do you keep yourself safe in this environment? How do you eliminate the risks that come with long-lived credentials? The answer is simple but powerful. You get rid of long-lived credentials altogether. Instead, you use short-lived tokens, tokens that expire quickly, leaving nothing static for attackers to steal. How would that work in practice? You bring in an identity provider, something like Auth0 or Azure Intru AD. Your browser or CLI authenticates through an authorization code flow. It gets back an OIDC ID token. That token is then passed to your backend, and from there it flows safely to third-party APIs. At every step, an OAuth 2 proxy validates the token. If it's valid, the system extracts only what it needs, maybe your email address, and nothing more. So what does this mean for you? First, no more static keys lying around in .aws or .ssh folders waiting to be stolen. Second, no more burning money on expensive credential vaults just to store secrets you don't even need anymore. Wouldn't you want stronger security and lower cost at the same time? That's exactly what short-lived tokens give you.
Cloud-agnostic tools often look attractive, don't they? You only need to learn one DSL, and you can provision and manage resources across multiple cloud providers. On the surface, that sounds like a dream for you as a DevOps engineer. But here comes the catch, and it's a big one. These tools rely heavily on state files, and state files bring more problems than they solve. Let me ask you, why does Terraform need a state file, but tools like CloudFormation or kubectl don't? The answer usually given is simple. Terraform and other agnostic tools don't own the resources directly, so they need a way to track them. CloudFormation, on the other hand, manages resources it defines, so it already knows their state. But what happens when you introduce an AI agent into this mix? Imagine an agent that is meant to operate autonomously in the future. Do you really want to deal with passing state files around, keeping them updated, and making sure they never fall out of sync? That would turn into a blocker, increasing complexity to a level where running the agent becomes almost impossible. And you know this pain already. State files take up storage, they add complexity, and many times they are simply wrong, out of sync with the actual resources in your environment. So the question is, before we step fully into the agentic era, can we eliminate the need for state files altogether? The answer may sound simple at first. Just enforce unique names for all your resources. And in fact, some private cloud setups already do this by generating names automatically from resource attributes. But here's the challenge. Those names often turn out to be long, complex, and far from human-friendly. And enforcing global uniqueness across multiple accounts in a cloud provider, that quickly becomes impractical. So, what's a better solution? We already have a proven pattern. Kubernetes enforces unique names within a namespace. CloudFormation enforces unique names within a stack. Both approaches limit uniqueness to a small scope, not the entire universe. Now imagine if cloud-agnostic IaC tools work the same way. If you, as a DevOps engineer, could rely on human-readable identifiers that are unique only within a module or stack, that would remove the need for state files entirely. And if an agent can check directly whether a resource already exists just by name, it becomes one step closer to being fully autonomous. So here's the takeaway. Eliminating state files is not just about making your workflow simpler. It's about preparing the ground for agentic AI, where agents manage infrastructure with less friction
and more certainty. This topic deserves a deeper dive, so we'll cover it in detail in a separate video.
Okay, let's walk through an example. What happens if you throw a prompt at a large language model and ask it to create a VPC, and you expect it to return a clean, structured response? Sounds simple, right? But let's break down what really happens behind the scenes. Ideally, if the LLM has access to a web search tool, it will start by searching the internet for the relevant documentation on creating an AWS VPC. Once it finds that documentation, it pulls the content back. Then it needs to parse and understand what it just retrieved. Only after that can it match your prompt with the right sections of the documentation. And finally, it converts that into a structured response. So while you only see a neat answer, in reality, the model is going through multiple steps: search, fetch, parse, understand, match, before producing the output.
Here's the issue with current generation large language models. Even when you ask them to fetch documentation through web search, they often miss the latest version. Or worse, they skip the search entirely and rely on outdated information buried in their internal knowledge. And as a DevOps engineer, you know what that means. The response looks structured, but the details can be wrong, and wrong infrastructure commands can easily snowball into broken deployments. So what's the smarter alternative? Instead of relying on the LLM to go out and search, you pass the documentation along with your prompt. By giving the model exactly the docs it needs, you cut out the uncertainty of web search. The LLM doesn't waste time trying to locate or interpret stale sources. It simply maps your request against the supplied documentation and produces the structured response. The result for you is twofold: much higher accuracy and dramatically faster responses. And when you're working in production, both speed and accuracy matter.
As a DevOps engineer, you know how broad your role already is. You're expected to be good at infrastructure, automation, CI/CD, monitoring, and cloud platforms. Now imagine someone asked you to also master every programming language back-end developers use, or to dive deep into data structures and algorithms like a computer science graduate. Would that be realistic? Not at all. It would be mission impossible, piling those on top of everything you already need to know. In the same way, it isn't realistic to expect developers to master a long list of deployment tools and frameworks just to get their applications running. Think about a typical developer scenario. A back-end engineer has a simple requirement. They've got a service running on port 8080, and they want to expose it at /service1 as part of a larger backend made up of multiple services. That's it, a straightforward need. But look at what's expected from them today. They may need to learn Helm to deploy on Kubernetes, or a command line tool to deploy on a container as a service platform like AWS App Runner, or Docker Compose to run it locally in containers. No developer actually wants to spend time juggling all these different tools. Just like you as a DevOps engineer aren't expected to learn front-end frameworks or master every back-end language, developers shouldn't be expected to learn deployment tooling just to meet a basic requirement.
Now let's look at a simplified approach with an AI agent. As a developer, you no longer need to juggle Helm charts, Docker Compose files, or platform-specific CLIs. Instead, you simply tell the agent what you want, either in natural language like deploy my service on port 8080 at service 1, or in a structured format like YAML, which can be standardized to capture deployment details. The agent takes that input and translates it into the right commands for the chosen platform. This approach gives two big advantages. First, you as a developer don't need to learn a different tool and syntax every time your workload runs on a new platform. Kubernetes, AWS App Runner, ECS, Docker, whichever one is in use, the agent handles the translation for you. Second, DevOps engineers now have the flexibility to switch platforms as needed to optimize cost, performance, or scaling, without making developers relearn the entire deployment process. The agent ensures the change is seamless for developers, while DevOps keeps control over platform strategy. So developers can focus on building services, and DevOps can make platform decisions without disrupting the flow. So after everything we've seen, rigid workflows, Too many tools, long-lived secrets, state files, and the complexity of platform-specific syntax. The big question is, what does this mean for us as DevOps engineers? Well, here's the truth. Employers everywhere are getting stricter about AI adoption. More and more companies now expect their engineers to use AI in their workflows, not just casually, but as a core part of how they operate. Okay, but what if you stick only to traditional infrastructure as code tools? The risk is clear. Your skills could start to look outdated very quickly. What you master today with Terraform or Pulumi could be automated away by an agent tomorrow. On the other hand, engineers who embrace AI as part of their DevOps practice gain two big advantages. First, they reduce the cognitive load. You don't have to juggle multiple CLIs, DSLs, and provider-specific works anymore. You work smarter, not harder. Second, you put yourself in a position to truly help developers. Instead of forcing them to learn Helm or Kubernetes add-ons or app runner commands, you give them a universal way to deploy and scale. You become the bridge that removes friction, not the gatekeeper adding more. And this isn't just about saving time. It's about staying relevant. Engineers who integrate AI into their workflows position themselves as AI-native DevOps engineers, flexible, adaptable, and valuable across platforms. Thank you for watching this session from MechCloud Academy. This is only the beginning of a larger journey. In our upcoming videos, we'll go deeper into how you can start building real-world DevOps workflows powered by AI and what that means for the future of engineering.